Hello, welcome to another video. So in this video, we're finally going to talk about scalars and vectors. So we've been dancing around it a while, these different terms and what they mean. So let's just go ahead and dive right in, and then this will set us up so that you can do virtually, well, not virtually, but like a lot of other things that use scalar and vectors, okay, in the future. So I'm going to start by defining what a scalar is and what a vector is. Okay, so a scalar is defined as any quantity, okay, that has only a magnitude, which is just another word for a value. Okay, um, and no direction. Okay, so this is something that you're probably familiar with in everyday life. They're typical numbers, 1, 2, 3, 4, 5. They're all just scalars. Um, your weight, like 10 pounds, is a scalar. It's only got a value, it doesn't have a direction. Temperature, that's another example of just a scalar. Okay. These are denoted by nothing special. Okay. As in, when you're looking at it in text, you just see a number, right? You'll just see 1. You won't see a bold, so no bold, italics, etc. Okay. Um, Anything can be done with them mathematically. Okay. Well, not anything. There's limits to what you can do, I guess, in some math, like, but anything can be done with them. That will do. Okay. What I mean by that is, like, you can add, subtract, multiply, divide. Okay. Um, these guys will combine units together. Okay. So for example, you've already seen this, right? If I have 10 meters and I divide it by 10 seconds, this is a 1 meter per second, right? If these guys tend to have units. Okay. Can use various, so they can use various mathematical properties. So we're talking they're commutative. What does that mean? That means that you can add them in any order that you like. Okay, so 1 plus 2 equals 2 plus 1. This isn't always the case in some other types of math, but you can do it here. They're associative, which means you could do like A plus B, group those, plus C, and that equals, A plus B plus C. You can also do A times B equals B times A, right? So you can do a lot of different stuff that goes with commutative. They commute, okay? Doesn't matter the order in which you apply. Okay, so that's a scalar. You're very used to this. This is what you do all the time just with like regular math, okay? But then I've slowly been introducing this term of vector, okay? So a vector is any quantity having magnitude and direction, okay? So this is the defining distinctive trait here. These guys will have a direction to them, okay? I.e., this is going to be your position, velocity, acceleration, force. Okay, there's a lot of things in Physics 1 that have this stuff. Okay, and so we'll be talking about these. Okay, these are denoted by a half arrow, i.e., so position has this. Whoops. Position has a half arrow over it. It's half because it's a pain to do that. Okay. You'll see in text. Okay. They might be bold, italics, something like that. Some way to identify that they are indeed a vector. Okay. They can have units. Okay. Just like scalars. Okay. So it could be like 10 meters. Okay, so you could say x equals 10 meters. So here's the unit part, and then it would say to the right. Okay, so it would have the direction part as well, but it can have units. Okay. Oops. They can be multiplied, or they can be added. Oops. They can be added and subtracted in any order, which is great. And then there is a form can be multiplied, and I don't like using this term because it's not the correct term technically, but there is a form of multiplication. Division isn't a thing. Okay, so they can't be divided. There's not a term for that. Again, so the various properties, as I was saying, you can add them in any order. So a plus b vector equals b plus a. Okay, you can add them in any order you want. You can also group. And you'll get the same thing. Okay. So these commutative and associative properties. I will say though, it does matter the order for the multiplying order in certain circumstances. Okay. And I'll talk about those as the semester goes on. Another property is that they can also interact with scalars. Okay, so it's not like vectors are only able to be to do math with just other vectors. You can actually perform mathematical operations with both of them. So, for example, you can have a scalar right here times x. Okay, and this changes the magnitude of x. Okay, it increases it by 10. So if x was this long times 10, it would look like that. Okay. So speaking of which, here's what a vector looks like. So a vector. This is the anatomy of a vector. Okay. I'll just go ahead and label this. This is vector A. This is the tail. And then the tip of the vector. This denotes direction. This denotes the source of the vector. So where's it coming from? Okay, maybe it's starting at the origin. You can then also write, maybe vector A. If you were to write stuff about it, you would say 10 meters to the right. And then if we overlay the coordinate system on there, plus x plus y, we could say 10 meters in the positive x direction. Okay. We could say 10 meters this. Okay, this guy's called a unit vector. And all it really does is it has a length of, so it's a vector with a length of 1. That just tells us direction, basically. I'll talk a little bit more about a unit vector and how you use them, I believe, when we do different mathematical operations with them, but this is another way to do it. There's also I, J, K, which work basically X, Y, Z, so you'll often sometimes see this. But for the most part, how I want you to, one good way that I really like to identify a vector and its direction is to say the length of it. So we would say, A equals 10 meters, and I would say, and 0 degrees relative to positive x-axis. And so what this means is that you're going to have a vector, okay, and it's pointing this way. And this entire coordinate system goes around 360 degrees. And you do it counterclockwise, okay? So if we're identifying different vectors, like this guy starts at 0. And so this is 0 degrees relative. If you wanted to say, maybe it's pointing over here, this particular vector, it would open up like this, and this would be like, I don't know, 120 degrees. And you would say vector B is 5 meters and 120 degrees relative to positive x-axis. You can also, instead of this, use, so for example, if you have a vector like this, you can say that you're marching out this many x's and going up this many y's. So maybe this is 3 and 2, and this is vector C, and you could say maybe C is like 4 units in length, and you could say 4, and then you would say off to the side you would say like 3x plus 2y, or 4, and 3i plus 2j, okay? You can also do it like this if you're just denoting direction, just like a typical XY system. So there's many ways to represent. The point of this is there's many ways to represent direction. I do tend to lean towards this. I think it's the most straightforward, especially because you may or may not be familiar with this type of notation. And so I think it's the easiest to use. It tells you the direction. It's good stuff. Okay. All right. Oh yeah, one other thing. If you want so say you have a vector, okay, just some vector, and it's like a length of, I don't know, 5 or something. I mean, you only care about direction, or only care about magnitude and not direction in this instance. You'd want what was just the magnitude of it, and so you would use absolute value bars, and you would say 5. Okay? So, just FYI, because sometimes you don't actually care about direction, you only care about magnitude. So, just a heads up. All right, so now let's do math with vectors, okay? We've got tons of vector stuff that we're going to have to do mathematically, so we need to learn how to do this. So here's an example. Let's do 1D math first. So we've kind of already been doing this, right? Like we've had cars moving to the right, and then maybe they have an acceleration to the left. but let's just do some more just generic examples so we're comfortable. So here's an example. A person walks 5 meters and then 6 meters. What is the resultant vector? Okay, this means the I mean it's in the name. It's the vector that results from two or more other vectors. Okay, so we want to know what is the resultant vector. This actually doesn't give us direction, so I'm going to real quick just add to the right. That way it's very explicit. So we've got someone, they're walking 5 meters. Okay, we'll just call this vector A. And then we've got vector B. And we want to know what is the resultant vector. So the resultant vector is going to be A plus B. Let's just call the resultant vector C in this case. And so we would do 5 meters. They're both pointing in the same direction. So if we define this as in the positive x direction, so we define a coordinate system, we would say 5 meters, pos x direction, there we go, plus 6 meters, I'll just do it this way, kind of inventing my own notation. This equals 11 meters positive x direction. And so you would get a vector C that kind of looks like this, okay, which is 11 meters positive x, okay? If you had, so how about this example? You have 5 meter to the right, 6 meter to the left. You would write this as 5 meter positive x direction plus 6 meter negative x direction. And then what you would do is you'd pull this out. And so it would be 5 meters plus x minus 6 meters. And because we've now moved this out, this becomes positive x again. That way, these are now the same thing. So we can now add the two together, and we get minus 1 meter in the positive x direction, or 1 meter negative x direction. Okay, so you can freely move this in and out of the parentheses, or however you're defining your direction. You know, you can write it like this. You can just have it with the x. You can do even I, right? You can use this. Okay, kind of the same thing. You can pull this in and out. You can also add these visually. And what I mean by that is this doesn't require any math, right? Here we got two vectors. Here, let's do it like this. So we've got two vectors like this. To add visually, first move, tip of one vector to the tail of another. So the great thing about vectors is This vector right here, if we move this wherever we want, as long as we don't change the orientation of the vector, so we can't like flip it, so we don't change the direction, we can actually move it wherever we want in space. And it's still the same vector, nothing changes. So what we're going to do is we're going to basically, so we had this vector, and I think we had, so with our example, we had this vector, and then we've got this guy over here or something like that. We're going to move this over here, and so it'll be boom, boom. So you move the tip, tip to tail, okay? And then you draw one more vector that encompasses both of them from the tail to the tip. So last step, draw from tail of first vector to tip of last vector, okay? And then that's your resultant. Okay. This is known as the tip to tail method. It's extremely popular because you can use it for multiple vectors at once. There's other methods to do this, but you can, like some of the methods, you only, or at least one method I'm thinking of, you can only use it for 2 vectors at a time. But this guy, say you had like all of these vectors, let's put them in different colors. We can line up all of these, and I can honestly do this in literally whatever order I want. Whenever you switch direction, again, remember tip to tail. We can just do this in any order we want. And then this is our resultant, okay? And again, any order works. So this will be my length regardless. So if I do, here, let's do black, red, then I'll do the blue, then I'll do the rainbow, then I'll do this like ocean thing, and then here, it's a little bit shorter, just because I'm not perfect with drawing the lengths, right? Like this blue is slightly longer or whatever. But keep in mind it works if you're able to do that. I mean, you must be saying, well, so here's the downside to visual, right? It's not perfect. So visual adding isn't perfect. It's really just meant to give you an idea of the final vector before you do the math. Okay? Anyway, that's 1D. All right? So now, that's everything we've done with kinematics, right? We've been doing one-dimensional vectors for a while. But we do have to move to two-dimensional vectors, okay? So how do we add this to this? Well, visually, it works the same way, okay? So we do this, tip to tail, boom. This is our resultant, okay? So tip to tail still works. So use tip to tail. But mathematically, what? Because you can't do, like, I don't know, 3x plus 2y, right? Like, what does that even mean? You can't add x and y together. So what do? The answer is you break vectors into components, okay? And you've kind of seen shadows of this, just hints of what I'm about to do already. So every 2D vector, okay, because we're talking about 2D specifically, every 2D vector has two components. It has an x component and a y component. Now, what is a component? Well, a component is how much of a vector lies in that direction. So if I have a vector that's this is vector A. If you drop a vertical shadow down, this is the x component. We'll call it AX, okay? And then you draw from there, tip to tail, this is our y component, okay? So AX and AY are the components of A. So the idea then is you have vector A and you want to add it to vector B, okay? So to add them, break each into components. This is step 1, okay? So let's do this. We have AX, AY. We have BX, BY. Great. Next, add AX to BX and AY to BY. So cool. Let's call it AX plus BX equals CX, and AY plus BY equals CY. Cool. Next, CX and CY serve as the components of the resultant vector. Okay, that's great. So we have our new components. Now we put them together. So if we want C equals CX plus CY. So if we want this, we use what's actually known as the Pythagorean theorem. Okay, so we'll actually C squared, right? It's literally a triangle. Okay, so C will be the square root of CX squared plus CY squared. Okay. Now, a couple other things is let's go ahead and do the geometry, okay? So I want to show you just a couple things. So this is going to be the general overview, okay? So you're going to break them into components, right? Then you add the components, then you do the Pythagorean theorem, and that gets you the net vector. You'll then do the last step is theta equals the arctangent of the y components over the x components. And I'll explain this as well, okay? So we need to do some explaining on the steps. So step one, how do we break them into components in the first place, right? I said, in step one, I said, well, we just need to break A into AX and AY. Well, how do you actually do that? So, we have A. We have AX. We have AY. If you notice, this is a right triangle, right? So that's 90 degrees. This is some theta, okay? So, if you're looking at any triangle, okay, this is the hypotenuse, and this is where trig comes in. Okay, this is the hypotenuse. Here's your angle. This is the adjacent side. It's the one underneath, okay, the angle. And then this opposite one is over here. So this is the opposite side to this, okay? So in other words, A is the hypotenuse. The adjacent side is AX, and the opposite side is AY. So if we had a relationship between AX, and A, remember we know A, okay, in this instance, and then AY and A, we could break them into components, which is what we want to do, right? So, luckily, you know, people have been working on this for a while. You know, the Earth's pretty old. People have been thinking about math and trig for a long time. And so, it's kind of solved for us, okay? So here's what we use. We use these trig definitions, okay? So, cosine of theta is defined to be the adjacent side over the hypotenuse. Sine theta is defined to be the opposite side over the hypotenuse. And tangent of theta is defined to be the opposite side over the adjacent side. Now, there's many, many more trig functions than this. If you look up sailing, there's a crazy amount. But in this class, we're really only going to use these three pretty much all the time. I don't even know of anything else that we'd ever use. So, but knowing these guys and being able to use them well is necessary, okay? So let's look at this then. Cosine of theta is the adjacent side over the hypotenuse. So the adjacent side is this, AX, so we just plug in, right, for adjacent. Here, let's write it like this. So this is AX over the hypotenuse. Cool. So let's write this out. We multiply this over, because this is what we're solving for. We want the x component, right? We're breaking these guys into components. So this is what it's equal to. Similarly, AY is equal to A sine theta. This is why in every problem ever, well, not every problem, but in a lot of problems, you relate cosine with x and sine with y. There's a couple instances, or at least one major instance, that we'll see during forces where these will flip actually, but I'll show you the geometry of that when the time comes. The other thing was tangent of theta. So this is why we used arctangent at the end. So we had this new resultant, right? We had, whoops. We had, here, let's just do this. Okay. So when we were combining them back together and trying to figure out direction, I said that you use arctangent. That's because we had a new cx and cy. And so we already had these, and we were trying to solve for c, the new vector. So this is going to be the opposite over the adjacent. Okay, and we wanted the angle, right? We wanted the angle of the new vector. Because we had just solved for this, we wanted the angle. So this was theta, was the arctangent of cy over cx. And arctangent is just how you essentially move this over. It's the inverse of it. You'll often see this written. I try to avoid this notation because to me that means this, which is a very different thing. So you'll see me consistently use arctangent. Some books don't, some books use this. My opinion is that it's not a good idea because of this. Okay. So I think I've kind of covered everything. So let's go ahead and just do an example, but real quick, let's just do the steps one more time and you'll see me follow the steps. So step 1, break into components. And you'll use ax equals a cosine theta, ay equals a sine theta. Cool. And then maybe other ones, bx, by, cx, cy. Step 2, add components. B cosine theta, B sine theta, okay. AX plus BX equals CX. AY plus BY equals CY. Step 3. Combine CX to get C, and this use this. And step 4, some people just keep it under step 3. Get direction. Theta equals arctangent of cy over cx. Okay, so now that we've got our steps, let's see how it works with an actual example. Okay, so I'm going to create, if I could here, a coordinate system. Oh, they already had one. I'm trying to just... Wow, this is amazing. Look at this. Cool. We're going to define this coordinate system right now as plus x plus y. Here's the question. So we want to determine the resultant vector of the 3 vectors. Okay, so we've got multiple vectors. Let's write them all out. So here's a very generic A, okay, 44 units. We're not told what the units are. and this is 28 degrees. We've got B, which is 56 degrees relative to the minus x-axis, so you'll see how we deal with that. And this is equal to 26.5 units. And then lastly, we've got this rainbow guy, which unfortunately they chose red, which was, I wanted to use this to get a different color. Why? Okay, let's use this guy. It also should be thicker. Can't see this. That's too thick. Like I'm spending all my time doing this. Okay, there we go. And this is C, and this is, they don't give us any angle, but we can see very clearly that it's forming, 90 degrees here. And this is 31. Okay, so we've got our three vectors. So, step one, break into components. All right. So, AX equals A cosine theta equals A is equal to 44. Cool. Cosine of 28 degrees. This equals 38.85. Okay, AY is equal to A sine theta equals 44 sine of 28 degrees. One thing, as I'm going through, make sure your calculator is set to degrees. They're typically set to radians, which is, in my opinion, I like using radians more, but for this class we'll all be using degrees, so make sure you set your calculator to this, okay? And you can test it to see if you're getting the right values. Okay, so we get 38.85 and 20.66. This means that this vector has this guy, which is 38.85, and then this guy, which is 20.66, and then this one was 44. These are the values that we just calculated, okay? All right. Next up, we've got our x and y of this. Let's do b. So bx equals b cosine theta. Now, one thing you may have noticed, and you may be screaming at me, what are you doing? These components pointed right and up, which are both positive. But this one points left and up, which means the x component of b should be negative. And so what we can actually do, there's two ways you can do this. You can do 26, so you can do 26.5 cosine of 56 degrees, and then write 14.82, and then say negative added because it points left, okay? Or if you want to mathematically brute force it, you can say b cosine theta, and then do this entire angle, which would be 180 minus 56 degrees. If you do that, you'll get the negative value. Okay, so two ways to do it. So you would do 26.5 cosine of 180 minus 56. Okay, so two ways to do it, however you want to do it. I kind of prefer this way because it's easier for me to visualize. I can see that this angle is right here, and I can see the adjacent side. This is clearly bx to this, right? Just like this was ax. But if you want to use this angle, it works as well. Okay. If you don't, if you just do cosine of 56 or whatever, you'll get the 14.8. You'll get the positive version. Okay, so you have to manually add that. Or, again, you can brute force it. By is positive, so we don't have to worry about that. And this was 21.97. Let me just make sure I'm boxing all of this so I know what to do. Lastly, we have C. Now, if you'll see C, there is no x component, right? There's no x. It points straight down. So Cx is actually just 0. But let's say you didn't draw it, and you don't believe that. You would do C 31 cosine of, if you remember, it was 90 right here. Another 90, so this is 180. Another 90, which would be 270 total. So you would do cosine of 270, and you'll see that this guy is 0. So you would get Cx equals 0 regardless. Cy is going to be all in the y direction, so it would be minus 31 because it points down. But again, if you didn't know that, you would just do C sine theta, so this would be 31 sine 270, and this would give you minus 31 as well. Okay, so either way, you'll get negative 31. So that's step 1. Step 1's the longest, and this is why working with vectors takes a lot of time, and that people don't like it, because you have to break everything in the components first, and then you can like start adding and putting stuff back together. So step 2 is add components together. Okay, so we're going to do ax plus bx plus cx, and let's just call this rx. This is the resultant vector. I believe it was 38, so we're adding 38.85, negative 14.8, and 0. So 38.85 plus a negative 14.82 plus 0 is Rx, and that equals 24. I believe that's roughly. Okay. Yeah, because 0.85, 0.82, that's 0.08, or 0.03. So it's roughly 24. The Cy's, or the Y's, this equals Ry. This will be 20.66 plus 21.97, and this is minus 31. This is going to be 11.6. Okay? Cool. So now we have our two components. So we have 24, so Rx. And then this guy is 11.6. Which means, tip to tail method, this is going to be our final vector right here. And this looks like, because we have two positive x and y, right? So if you were using, Cartesian right here, you'd be plus x plus y. This would put us in the first quadrant. Right? So our answer, our angle that we ultimately get for this should be between 0 and 90. Anyway, let's get the value. 24 squared plus 11.6 squared. And this is 26.7. So that's our magnitude. Now we just need our angle. Ry over Rx, so this would be 11.6 over, 24? And this gives us an angle of 25.8 degrees. Okay, so this is between 0 and 90, just as I said. So our final answer is So R equals 26.7 and 25.8 degrees relative to positive x-axis. Okay. So here's our final vector one more time. And again, here were our steps. We broke 3 vectors into their components, x and y components. Then we added the x components together, added the y components together. Then we did the Pythagorean theorem right here, put them all together. We got our magnitude of the final vector. We got the value of the final vector, right? And then we got the angle. Okay. I will mention there is an instance where arctangent doesn't work. I typically stray away from those problems, but you can see for us, right, we had an arctangent, for example, of 11.6 over 24. But if these were both negative, in other words, if these all lied in the third quadrant, sorry, then this would yield a positive, and we would get, we would still get 25.8 degrees. But what that means is that you just need to do a 180 to get the final vector, okay? Because this is also 25.8 degrees. Because alternate interior angles are congruent, if you remember some geometry, okay? Right? That's what it would look like. This is our real vector. This is what 2 negatives would also yield, okay? So do be careful on direction, but if you're doing the visual method, the tip to tail method, and you know what you're looking for, you know your vector should have been down here anyway, okay? So just be careful. There are some things that can trip you up, but I have no doubt that you should be able to master this, okay? So thanks, and I'll see you in the next one.